Okay, so I hope you had a good weekend. Let's get started. So I'm on Zoom and I push the record button, so hopefully we're doing it right. Last time we talked about mean field theory, and we introduced, using very, very simple mathematics, some ideas about what happens near a phase transition. We discovered that mean field theory is actually really good. It predicts that there should be power law dependencies on various thermodynamic quantities. Predicts universality, meaning that all these exponents don't depend on anything such as coupling constants like the spin interactions. They're just known functions. We predicted, in fact, that thermodynamic data between different variables will collapse onto a universal curve. And we discussed that we can predict actually phase diagrams. Things that we found that were not so great about mean field theory was we discovered that the exponents are not quite correct when we compare them with exact results or computer simulation or the normalization group, and they don't really capture the dimension dependent. Or I should say it is possible to develop variations of mean field theory which do have some sort of dimension dependent. So here on the right-hand side, I have reminded you about what we did. We worked out the equation of state, which is this equation in the middle, h equals mt plus a third m cubed. And I showed you, just by looking at it, that we could write it into this universal form, t to the beta delta times a function plus or minus, depending on whether you're above or below tc, of m over t to the beta, where I've substituted in the mean field exponent, beta equals a half for the order parameter, and delta equals 3 for the exponent that tells you how the linear response theory breaks down at the critical point. And so the induced magnetization is actually proportional to a power of h that's not 1, which is a prima facie breakdown of Curie's law. And what is the significance of that? Well, the significance really is that the magnetization is now not just a function of two variables, as you might expect, but it's a prefactor times a function of just one variable, a combination of variables, which I'll refer to as a similarity variable. And so you might say, well, this is kind of like what we saw in dimensional analysis when we were looking at what happened for the shallow water wave. I wrote down for you the exact formula from fluid mechanics, and I showed you that we could guess the asymptotic behavior for shallow water waves, the speed going as the square root of the depth of the water, by just assuming that the depth was small compared to the wavelength, and then we could remove the wavelength from our description of the system, and then dimensional analysis, just on its own, gave us the exponents. And so the question is this really the same thing that is happening? And I'm going to get into that in just a moment. So the first thing is I want to show you, answer the question, well, does this prediction actually work? I haven't shown you that up to now. So here are experimental data. These are experimental data on 5 different magnetic materials, and the horizontal axis and vertical axis are plotted in the way that we're predicting. So this is scaled magnetization. By that I mean m over t to the beta, and scale temperature, I really mean T over h to the power 1 over beta delta. So that's what the theory is predicting. And you can see data from 5 different materials, it's listed in the caption, and you can see that all those data are both above and below TC for these 5 different materials. They all fall into one curve. You wouldn't know that it's 5 different materials. And I don't know if you can see it very well, but here you can see there's a solid line through here. So this is the universal scaling function. And this isn't from mean field theory. So this is actually the renormalization group prediction for that. And we've used the renormalization group prediction for the critical exponents. So you can see it's absolutely amazingly successful. And so now the question is, well, is this just like this dimensional analysis that we've seen before in homework 1 and in class? Now, I don't know how many people here did all the homework questions or did this particular question, but if you look at the homework sheet, there was one particular question, homework 1.4, where I invited you to solve many body theory general using dimensional analysis. So what we did in that homework assignment, optional homework assignment, was take an interacting gas, assume that we can write its, we consider a class of materials where the potential energy follows a form like I'm showing over here on the right. So basically, the potential energy depends on a range sigma and a binding energy epsilon. And the only thing that's different between different materials is they have different values for epsilon and sigma, but they have the same functional form for this pair potential. And it could be modeled by a Leonard-Jones 612 potential or something like that. There's many other choices that people use. But once you have that, then what you are able to show quite easily, the question leads you through it, is just starting from the partition function and just using dimensional analysis, putting things into dimensionless form, is that one can show that the whole many-body problem exactly follows the form that I've shown over here, called the law of corresponding states. And in the homework, you actually use dimensional analysis to do a calculation that would be extremely hard to do by any kind of calculation other than dimensional analysis. So that's called the law of corresponding states, and I'm going to show you how that works. So here at the top here, we have the data collapse for renormalization group universal scaling functions for a magnet at the critical point. Let me now show you the law of corresponding states. So in the law of corresponding states, you divide the pressure or the density by the critical density, you divide the temperature by the critical temperature, and then you plot data for different materials as shown here, and was first done by Guggenheim in the 1940s. And you can see that all these data, again, fall onto one universal curve. And so that was a big surprise when it was discovered, and it was called the law of corresponding states. And you might ask yourself, well, that looks very interesting. This is what's plotted on the horizontal axis. Not sure if you can all read it. This is the density divided by the critical density. So the high density part over here. So if you, for example, said, well, let's choose a temperature less than Tc. Let's say this temperature, then there's two coexisting phases like that. That's the high density phase. So this would be the density of the liquid. This would be the density of the gas. They're in coexistence. And I can then just read off from this graph what their density is. And you might say, well, the shape near here, we in the first lecture or second lecture, we estimated that using our 10-second theory, and we said, well, this should be a parabola. It should be a parabola, so this should look like a square root dependent. But you can see from these data that actually this curve is rather skewed, right? You can see it doesn't look like a parabola. It's skewed more to the right than to the left. And if you look down at the bottom, well, I've made an annotation. Look at equation 6.4. Guggenheim fitted these data with a curve. He just said, well, I don't know what this is. It obviously isn't a parabola. Maybe it's a cubic. So he just fitted a cubic to it. And this exponent is roughly a third. And if you remember, I showed you that the 10-second theory actually doesn't quite agree with experiment. And the experimental results are more like 0.32, something like that. So close to a third. So you can already see that in these early data. So this is called the Guggenheim plot, and this is called the law of corresponding states. And it was derived, and Guggenheim, in fact, understood how to derive that by the dimensional analysis method, something related to what I made you do in the homework. So are these things the same? Well, they're not, and I want to explain to you why. So the first thing is that those two scalings, they look like data collapse, so that they have the same, you can call them data collapse, but the Guggenheim plot is an exact result for all gases that have the same functional form. So this applies not just near the critical point, but everywhere. Okay, so that's the first thing, and so the data collapse that we're talking about here in the phase transition context, that really only applies near the critical point. So this is an asymptotic result that is different from that. The second thing is that, as I'm going to show you, and as you've probably already seen, the results that we're obtaining could not be obtained by dimensional analysis. So these exponents, the values that we have, are not those of dimensional analysis. Okay, so what are we going to do today? So up to now, we've avoided the topic of correlations in space. So today we're going to put in space. So what we're going to be doing now is looking at how space is described. We're going to talk about correlations, and then we're going to talk about how you relate the spatial structure of a statistical mechanical system to thermodynamics. So up to now, we've talked about phase transitions as just being manifested in the thermodynamics, the heat capacity, the susceptibility, the magnetization per spin, so free energy. But of course, we can do spatially resolved studies of systems, and so we can look at the spatial correlations, and we're going to see that not only can we do that, but actually the two things are related, and we're going to find an extraordinarily useful connection between them, which is going to help us understand where the scaling laws come from. So I would say that our goal is to quantify correlations that describe spatial heterogeneity. And that spatial heterogeneity, we know if we were to look at it, we took a snapshot of the system, we might see something like this. And I'm just making stuff up as we go along. So that might be what you would see at some, time equals 1. And then let's suppose you look at some different time t equals 2. Well, now you might find something completely different, a completely different spatial structure. And so the spatial correlations depend on space, of course, because they're spatial, but they also depend on time. And so we want to understand, for example, what are the probability distributions? The probability density that tells us the probability of observing a particular spatial configuration. In space. What just happened? So in principle, one can also do this in time, but in this course, we're just going to be looking at equilibrium. So that's the first thing that we want to do, and the second thing that we're going to see is that there is a connection between the thermodynamics and the spatial correlations. Okay, so let's get started. And so I'm going to be following section 3.7.2 from my book. So what we're going to look at is the 2-point correlation function. And I'm going to define that in the following way. So this is so when I write down Ri, I mean the spatial location of spin I. And when I write down these angle brackets as usual, these are now our familiar thermal averages. So I want to show you how one can compute this in the way that we usually do in statistical mechanics, which is by taking derivatives of the partition function. So the so next thing we want to do is compute by differentiating the partition function. So to do that, I'm going to add an external space-dependent field. And so that's how we will compute this. So for now, let me just do it in a slightly simpler way. So for now, what I'm going to do is I'm going to write down the Hamiltonian as minus beta j sum over nearest neighbors si sj minus beta h si, and then later we might write this in another way as a beta times the sum over I hi si. But for now, for what I want to do next, we don't need to do that. So then I can calculate the partition function. So the partition function, just to remind you, is then the trace over summing over all the degrees of freedom of e to the beta j sum over I and j si sj plus beta h sum over I si. Okay, so that's my Hamiltonian, and if I want to compute the magnetization, so I want to compute this object, then I can get that in the following way. I can write that as, by definition, 1 over z and the trace over all my degrees of freedom of the following thing. First of all, the thing I want to average, which is the sum of ISI, then e to the minus beta times the Hamiltonian. Okay, so that's the basic statistical mechanics setup. Now, what I want you to note is that I can get this object by doing the following. I can take the partition function, and if I differentiate it over here with respect to h, if I differentiate z with respect to h, that is going to bring down this whole factor here. It's going to bring this factor down into here. Okay, so that means that I can write that this object here is dz by dh, and then I've got my factor of 1 over z, which is for the expectation value over here. That's this factor over here. And then when I differentiate with respect to h, it brings down a factor beta, and so I want to get rid of that, and so I will divide then by another factor of beta. So this object over here, this derivative, is in fact just this the sum over the total magnetization of the system. Okay, so does everybody see that manipulation? Anybody worried about the differentiation through the summation and the trace signs? Anything? Any questions? And any technical questions about that before I go on? Okay, so then what happens if we do this again? So we can repeat this. So for example, if I want to compute the sum over I and j of Si, Sj, well, I can do that again just by doing another derivative. If I differentiate again, so then I will get another factor of beta. So I'm going to have 1 over beta squared. I've got 1 over z, and then I've got d2z by dh squared. Okay, and remember that I and j are dummy variables. So they're just variables that are the same variables in here. This is also a dummy variable. And so just differentiating with respect to the overall magnetic field brings down those factors. Okay, all right, so everybody happy with this? Okay, great. So now let's now look at the isothermal susceptibility. So last time we introduced this. So the isothermal susceptibility, that's defined as dm by dh at constant t, and since m is this thing over here, this thing is m times the number of spins. That's n. M is the magnetization per spin. So m is a minus 1 over n df by dh. So that means that the chi is nothing more than d2 by dh squared, the logarithm of z, and then 1 over beta, and then 1 over n. Okay, so all I've done is take m is equal to this first thing over here, and then differentiate it one more time with respect to h. When I differentiate one more time with respect to h, I get d2z by dh squared. So that's where this formula comes from. So let's have a look at how what happens next. So this chi is 1 over n, 1 over beta, d by dh, and then inside I have the magnetization, which is 1 over z dz by dh. And so what I get is 1 over n kBt times 1 over z d2z by dh squared minus 1 over z squared dz by dh dz by dh. So what I've done is I've simply taken my definition of m and then literally just differentiated with respect to h, and that gives me the result I've shown here. Actually, why did I write this up here? Yeah, no, this is correct. That's correct, and then this is this derivative. Yeah, that's right. Okay, so then if I work this out, so now I can write down what these things are. So I'm going to the factors of 1 over kBt. This beta squared then gives me this as 1 over kt, and then what I have in here is the sum over ij, si, sj, and then minus the sum over I, si, squared. So just reading off what this first term is and what the second term is, then I can see that chi is the sum over ij of this object over here. And so I can write this then as 1 over n, 1 over kBt, and then this object inside this summation is actually nothing other than the correlation function at the top here. So this is then G of Ri and Rj. Okay, so this is an exact result. So it tells us that the correlation function is related to the susceptibility. Okay, I'm going to say a little bit more about what the correlation function means physically, but now let me just make a further simplification. So in thermal equilibrium, the correlation function between the spin at site I and the spin at site J is actually translationally invariant. So everything just depends on the distance between the sites rather than the site values themselves. And so this becomes a translationally invariant. So what that means is if I look at the difference between Ri and Rj over here, and then I go to the next site, the next one, and the next one, as long as they're separated by the same amount, they will give you the same contribution. So when I do the double sum of I and j, what I'm going to get is n times summing over just one variable. So therefore, what's going to happen is that this is equal to 1 over n, 1 over kBt, and then n times the sum over just j goes from 1 to n. So now only one summation, and then g of Rj. And then those factors of n cancel out. And so then what I get is that chi t is equal to 1 over kBt times the sum over j g at the site Rj. So that's exact. Okay, so let's imagine that I'm looking at this on a lattice like so. So there's my d-dimensional lattice. Let's suppose the lattice spacing is a, and this is in d dimensions. So it's kind of inconvenient to write these things as a sum. So basically what I'll do is I'll turn this sum into an integral. So I do that by saying that sum over I is just the integral dr over the spacing, lattice spacing a. So this is going to end up being d dr over a to the power d times the 2-point correlation function as a function of r. And that is our final result. So this thing is called the static susceptibility sum rule. So why is it called that? Well, it's called the static susceptibility because this thing here is the static susceptibility. It's static, there's no dynamics in here. It's just telling you how the system thermodynamically responds. And then when we use this term sum rule, what that means, it usually means an integral over something. And so here we have this integral. And so that's why it's called a static susceptibility sum rule. Now, why do we care about this? And who cares about the correlation function anyway? So let's answer the so what question. So yes, go ahead.
So we simplify this pairwise, let's say, correlation function, because the argument there is it like because it doesn't depend on the positions, like relative. It only depends on the relative positions of the between the spins, such that that's why we simplify this correlation function to only the distance between the spin. That's why we
That's right. That's right.
That's why we're going to one.
Yeah. So it wasn't. So if it was translationally, if it was not translation invariant, I'd be summing over both the spin I, the first spin, and the second spin j. But because this function only depends on the distance between them, then if I just choose one spin and then look at sum over all the distances between it. And then once I get that, then I did it for all the other spins, I would just get n times what I started with. And so that's the simplification that you get. Okay, all right. So what I'm going to so the answer to the so what question is the following. We're going to see that this will help us introduce a quantity called the correlation length. And we're going to see that this gives us a connection between thermodynamics and space. Okay, so before we do that, I'm going to need to explain to you what is the meaning of the correlation function. So up to now, all I did was I told you this is it, I defined it, and I did some algebra, and I claimed that this thing, which I defined for no good reason, I just woke up one morning and decided this would be a nice thing to calculate, turns out to be related to susceptibility. So what does it really mean? So let's have a look at the thing that I defined, and I'm going to write it in this translation invariant form. So I defined this thing to be this. Okay, so it's just an object and you have to remember what it is. But actually, if you look at this carefully, you can see that this is really the following object. Si minus the expectation of Si times Sj minus the expectation of Sj. Okay, so can you all see that? Let's see where that comes from. So if I multiply this out, if I check, so I get expectation of Si, Sj, that's the first term, this times this. Then I have this thing times that. So that's going to be minus the expectation of Si times the expectation of Sj. And the expectation of Sj is just a number. Let's say it's 3. So I can just, so when I work out the expectation of Sj, it's just the expectation of Sj. So this is equal to this thing here is just minus Si Sj. Okay, and then I do the other terms. So then I have this term multiplying this. So now I get expectation of Si times Sj like that. And this thing is just again Si Sj. And then I get minus with a plus Si Sj like that. And so now I get minus 2 plus 1, and so that all ends up being equal to Si Sj minus 1 factor of Si Sj. Okay, so those two things are the same. And what is the significance of this object? Well, this object over here, this is just the fluctuation. So it's the expectation value of delta Si times delta Sj. So delta Si means the fluctuation of spin I about its mean value Si. So that's what we call the fluctuation. That's the terms that we neglected when we wrote down mean field theory. So it's the difference between what the value of the spin is, looking at it, and what the average value is. So that's so delta SI is how much spin I is different from its mean value. That's the definition of fluctuation. And so what does G tell us? G of Ri minus Rj, what that tells us then is how much the fluctuation at Ri resembles the fluctuation at Rj. So that's what it's telling us. It's some measure of how correlated are the fluctuations I see over here and the fluctuations I see over here. If they have similar values, then I'll get 1. If they are uncorrelated, then when I do the average between the fluctuation at site I and the fluctuation at site j, so let's suppose site I is over here, site j is over here. They're just both fluctuating like this. Sometimes I take the average and one is pointing up and the other is pointing down. Sometimes it's the other way around. They're not correlated. I'm going to average. I'm going to get 0. On the other hand, if they're always fluctuating together, when this goes up, this one goes up, down, up, down, up, down, then I'm going to get 1 all the time whenever I average. And so this thing, that's why this thing is called the correlation function. Okay, now later we're going to learn how to calculate this, but not right now. So what I'm going to do now is I'm going to tell you a result. And the result should be relatively not surprising to you. You might say, well, okay, how correlated are these spins going to be? If they're very close together, close spins, we would expect them to be very correlated. And then far away spins, like I've got one spin over here, another spin on the moon. This one's fluctuating up and down. The one on the moon is fluctuating up and down. There's hardly any reason why they should be in contact with each other. So we'd expect them to be completely uncorrelated. And so then you might say, okay, so that's my intuition. Well, if I think that, when I say close and far away, the question is with respect to what? So there should be some length scale that tells you what that is. So I'm going to say a length scale called the correlation length. And this length scale we will refer to as the correlation length. So psi is equal to this correlation length. And there's no reason why it shouldn't depend on state variables. Like, for example, I've been looking at a physical system at temperature T. The correlation length can vary with temperature T. So that's what we would expect. And so if I know that there's a single length scale, I know that the correlations, if I plot distance, if I plot G of R, I know it's some decaying function like this with some characteristic scale psi. Then what you'd say is, well, your guess would be, oh, this should be maybe some exponentially decaying thing. So that would be the simplest guess that you would make. And it turns out to be completely correct. So actually, what you can calculate is that a G of R goes like this. It goes as E to the minus R over psi divided by, hopefully I've got these numbers, these factors correct. It goes something like this. Now, this isn't the full functional form. This is an asymptotic form. So this is true when R is much larger than the correlation function. And it's also true when T is not equal to TC. So that's the result. Okay, so we'd like to know the full functional form for this, and we can actually calculate it in terms of Bessel functions, but we don't need to know it for now. Now, why do I care about this? Well, let's have a look at our static susceptibility sum rule. So here's our static susceptibility sum rule over here on the left-hand side, and the isothermal susceptibility is related to an integral of the correlation function. That integral is over all of space. So when I do that integral, it's going to go out to the far distant space. And the question you should ask yourself is, well, is that integral going to converge? Well, so if we look at the static susceptibility sum rule, so we know that chi of t is equal to 1 over lattice spacing a to the d, kbt times the integral d dr of g of r. And we know that g of r decays exponentially. As r goes to infinity. And so we know then that that integral is going to be completely convergent. So that's good, right? You want integrals to converge, but it's bad actually. Okay, I tricked you. You all were nodding your heads and saying yes, it's great that the integral converges. This is a course on phase transitions and renormalization group. So the thing that sparks joy in a course like this is not when things converge, it's when things diverge, when things go to infinity. That's what we want to see happen. And in fact, we know that that happens because this is actually bad news. Why is it bad news? Well, I spent a lot of time last lecture showing you that, at least in mean field theory, chi t in mean field theory goes like 1 over kb times t minus tc. Above and below TC, it's the same thing, but with some other factor of 2. So in other words, i.e. T minus TC over TC to the power minus gamma, and in our case, in mean field theory, gamma was equal to 1, although it's not 1 in general. So that means that chi actually diverges. Chi diverges at TC. Okay, that you knew, but the right-hand side is always convergent. This thing over here is always convergent. So how can a diverging quantity equal to a converging quantity? Okay, so and this quantity, you can say, well, this quantity is only an approximation. No, it's exact. Okay, there's no room for error here. So what happened? How is it possible? How can all of these things that I've told you be reconciled? Anybody got any ideas? Mm-hmm. Yeah.
It might still have some correlation. not exponential.
Okay, so remind me your name again.
Hold on, HD.
HD.
Yes.
Okay, I should remember your real name.
Yes.
How? Haldong.
Yes.
Okay, I will eventually get your names right. Haldong says, well, maybe the correlation function isn't really exponential at t equals tc, and of course I hinted that, so that's true. Okay, now are you going to say something? Okay, let's hold the question, but you're going to say that you're going to do a +1 for what Haldong said, right? But the correlation length might not be. The correlation might not be defined. Definitely, you both of you are on the right track. Frank, you had a question. What's your name, by the way, again? Palka. Thank you. Okay. Frank.
The assumption of R much greater than correlation length does not.
Okay. And how could that happen?
Well, the correlation length and spoiler.
Okay, so if you know the answer and you know that you know the answer, then okay. So so of course so what is happening is that as t goes to tc, the correlation length can go to infinity, in which case this e to the minus r of xi can't be correct. There must be other subdominant terms. And so so the answer is that the correlation length must diverge. Okay, so let's see how that can happen. If we think so what we've said is that as t goes to tc, the correlation length gets bigger. So there's two things there. One is at tc, the correlation length is infinity. So this is just what Haldong said, namely that at tc it's not an exponential. But suppose we're getting very close to tc. Okay, it's still exponential, right? But it has this, but something else is happening. So the question that we want to ask next is, as t goes to tc, how does psi change? Okay, so in other words, what I want to say is, for t equals tc, the e to the minus r over psi might break down. And indeed it does. But for t close to tc, e to the minus r over psi does not break down. So I still have a puzzle. Knowing that it diverges at infinity, is formally infinity, I still want to know how is it that the thermodynamic susceptibility can behave as this asymptotic form 1 over t minus tc. So let's go ahead and calculate how that can happen. So what is the strategy to answer this question? So the next thing we're going to do is this. We're going to put chi goes as t minus tc to the minus gamma with gamma equals 1 on the left-hand side of the static susceptibility sum rule. And then we're going to evaluate the integral on the right-hand side. And that should enable us to find, well, how does psi depend on t? So that's the strategy that we're going to do. So let's go ahead and do the integral. So on the left-hand side, I have t minus tc over tc to the minus 1. And now let's do the integral. So the integral is the correlation function. We're going to ignore the fact that we're on the lattice. So if I ignore the fact that we're on the lattice, then the integral is rotationally symmetric. So I don't know the crystal lattice structure. So I'm looking at distances larger than the correlation length. So all the integrals are rotationally invariant and converge. So then if I'm looking at the integral d dr, that is just proportional to the surface area of a d-dimensional sphere times the integral from r goes from 0 to infinity, dr, r to the power d minus 1, e to the minus r over xi, and then I have the normalization of the correlation function, which was, actually I've done this wrong. Let's try this again. I have this, and then the denominator is r to the d minus 1 over 2 times xi to the d minus 3 over 2, like that. So that's the integral that I have to do. And I'm going to do this by a usual trick. So the trick that I'm going to use to evaluate this integral is I'm going to define the variable z is r over xi. And then in terms of that variable, I'll do the change of variables. Oh, and by the way, this thing here is the surface area of a d-dimensional sphere. And then, so now that what happens to this integral, so this integral now becomes, I claim is equal to this, apart from this surface area, I have xi squared, and then the integral from 0 to infinity of z to the power d minus 1 over 2 e to the minus z dz. And so this thing over here on the right-hand side is some number, which depends upon dimension, but it is convergent. It's related to the Euler gamma function. And so the important thing is I don't care about the surface area and things. What I've just derived is that xi squared is proportional to t minus tc over tc to the power minus 1. And so what does that tell me? That tells me then that we've just predicted that the correlation length as a function of t goes as t goes to tc as t minus tc over tc to the power minus nu, and that power nu is equal to 1/2. So the correlation length does indeed diverge as I get closer and closer to the critical temperature, and that means that the spatial correlations grow in range. So spatial correlations grow in range as t goes to tc. And last time we talked about the divergence of the susceptibility, we said basically if I'm close to tc, well, below tc, the system spontaneously orders. Above tc, it doesn't. So if I'm sitting exactly at tc, then any small nudge will make the system order because it's already on the point of ordering. So in some sense, we now have a spatial analog of that. So now the spatial correlations grow in range. I'm going to plot them in a second. So then you might say, well, that's fine, but what about what happens at tc? T is exactly equal to tc. So I'll tell you the answer, but I'm not going to derive it for now. So g of r at tc is equal to this, some number times 1 over r to the power d minus 2 plus eta. And so this eta is another critical exponent. And it's very small. Actually, in mean field theory, as we'll see, mean field theory says eta is equal to 0, and what renormalization group tells us is that eta is about 0.01, at least in 3 dimensions. Okay, so we have a power law decay as opposed to an exponential decay. So basically, at TC, correlations decay algebraically So if they decay algebraically, that basically means that they're decaying slowly. And exponential means that they're decaying fast. Okay, so that's the result. Now you might say, okay, so I have a function that decays exponentially, and then bang, as I go to the critical point, suddenly it decays power law-like. And that's in some sense the way that it is sometimes presented in books and so on. But it's as they say in Russian, it's not quite correct. So let's talk about what is actually going on. So here let's draw the on the vertical axis the correlation function. So G of R versus R, like so. And what I told you, and I made it plausible by saying that there should be some length scale, is that we know that at large distances, this thing should decay exponentially. But what happens at small distances, and actually what small distances is actually, it does something a bit more slow. So this is a slow decay, and then this is the fast decay, and then this scale over here is the correlation length. So in fact, at small r, this behavior here actually is going like 1 over r to the power d minus 2 plus eta. So this slow decay at small distances is a power law. At large distances, it goes exponentially. Now, what is happening then is as I go towards the critical point, so let's say that this picture is true for t is t1, which is considerably greater than tc. So then I'm making a measurement at some point. So suppose I measure at this distance. So I say, okay, I'm going to take 2 spins. They're going to be, 300 angstroms apart. I'm going to go and measure what is the correlation function at 300 angstroms. Now let's suppose I change the temperature. So now I'm looking at a different temperature, much closer to TC. So here is my distance R0, the same distance I had before. But now what's happened, I've gone to a scale where the exponential dependence switches on here. So now here is e to the minus r over xi. Here is 1 over r to the d minus 2 plus eta. And the correlation length at this temperature, xi T2, is much larger than this R0. So T2 minus TC is much less than T1 minus TC. So T1 is much larger than TC, T2 is not so much larger. And so what's happened is at the physical distance that I'm measuring, all that's happened is the correlation length has moved up in scale to beyond what I'm measuring. And so I feel that I've seen a change from exponential to power law, but all that's happened is I'm probing the distance, the difference between the large asymptotics of the function and the small asymptotics of the function. So what I would measure, so I would measure it at this distance in R, and what I would see is I would see exponential decay. And then now at this distance over here, what I'm going to measure, I will measure power law decay. So that's what's happening. So let's just summarize then what I've just told you. So the summary is that one, thermodynamics is connected to spatial heterogeneity by the 2-point correlation function. I've told you that there is a length scale psi of t, and I've shown you that the static susceptibility sum rule implies that psi of t goes to infinity as t goes to tc, and we computed the behavior. Okay, so that's all great. But now let's ask ourselves what this means. So remember when we were doing mean field theory, what that means is that spins feel some average value around them. So the mean field theory spins experience some average field. And then we computed what that is in a self-consistent way. But now what I've told you is that as we go towards TC, we actually go towards a regime where the fluctuations are no longer decaying rapidly with distance, but actually they're decaying slowly. So that means things are highly correlated. So that means that the fluctuations are much stronger than you would have otherwise expected. So what that means then is that what we've discovered is that correlations of fluctuations are strong and in fact get stronger as I go towards TC. So if that's the case, if there's fluctuations that are correlated and they're strong, then that means that mean field theory is now going to break down. In other words, there are strong fluctuations, and therefore the idea that I can say everything is more or less the same average value, that idea is going to go down, is going to go down the tubes. So basically what this implies is that mean field theory must break down as t goes to tc. So what I want to do next is I want to explore how mean field theory breaks down. Yes.
I was a little confused by the function of g of r.
Yeah.
In terms of the units, does it take that unit 1 over n d minus 2?
Yes. Well, I'm actually I'm actually not confident that I didn't make a mistake in copying down this formula here. So I will come to the dimensions later. The dimensions should be it should in the end go as length squared. The actual yeah, it should go as length squared. I don't know if this one does. I worried about it when I wrote these notes last time, which I'm copying it now, and then I persuaded myself that I got it right. So let's come back to the question of what the dimensions are, because there's no way I'm going to be able to fix an algebra mistake in real time. I will explain that. But it will go as length squared, but I'm going to be defining what the variable is that it's correlated in a particular way. Okay, so I won't be able to show you that right now. Okay, so how it's defined right now, I will double check that I copy down all of the right factors here, but we will be very careful about what the dimensions of it are later, and those I'll get exactly right. Okay, so what I will end up doing is I will be defining a rescaled spin variable, and that in units of those rescaled spin variables, then the correlation function will be length squared. Okay, but I will explain that. Okay, so. And I will check before next lecture. Okay, so so what I want to do next is I want to show you how we're going to measure the breakdown of mean field theory. So this is now going. I'm going to follow chapter 6.1 in my notes. I'm going to show you how a mean field theory, how to measure the mean field theory breakdown. As T tends to TC, so we can actually measure it, and we're going to prove that it breaks down, and we're going to see exactly how it breaks down. So here is our strategy. So what I'm going to do is I'm going to construct a measure of the relative importance of fluctuations. And I want to do that because when we did mean field theory, we threw away fluctuations. So that's step one, and then step two is I'm going to use the static susceptibility sum rule to estimate this measure. And so what I'm going to do is we're going to use mean field theory. We're going to calculate an object, which is assumed small in mean field theory. And then we're going to see, is it small? And if the answer to the question is yes, then that implies that mean field theory is self-consistent. And if the answer is no, then it means that mean field theory is not self-consistent. In fact, we'll see that mean field theory predicts the seeds of its own destruction. Being very dramatic here. Okay, so this is the best sort of theory. Okay, so or if you want to make a theory of something, that theory should tell you in what physical regime it works. Okay, you don't want a theory that always works. Okay, so for example, a theory that always works would be quantum electrodynamics. Okay, a renormalizable field theory. It never tells you it breaks down at high energies, whereas real field theories break down at high energies. They turn into something else. It breaks down into electroweak theory, and, ground unified theories, and string theory, and whatever. You want physical theory to tell you when they break down, not it's always going to give you an answer. Okay, because if it's going to give you an answer guaranteed, then it's going to have to end up being a wrong answer at some point. So with the whole idea of renormalizability as a criterion for physical theories, that was an important idea in the from the 1940s all the way up to the 1970s and 1980s. But by the 1990s, people realized no, this is all wrong. And if you want to read about that, I wrote an article last year for a book called 50 Years of the Renormalization Group, which talks about that, and you can find it online. Okay, so let's go and do a calculation. So let's now construct our measure. So remember that what I did last time. This is how we did mean field theory. So what we did was I wrote down the Ising Hamiltonian. So there's the Ising Hamiltonian. I wrote it down as in this form, minus H J Sj, and this site-dependent effective field Hj was H plus the sum over nearest neighbors I and J, I times Jij. So that was the exact result, and then we threw away the fluctuations. So then I wrote down that H is equal to H external field, not that H. I wrote too quickly here. Okay, so what we did was we threw away a term that was proportional to Sj minus the average of Sj. So we threw that term away, and so we ended up with an H, which is spatially uniform, and that was our mean field. So that was the strategy. So the question we want to ask is, how big is the neglected field? How big is the neglected term? I.e. the fluctuation delta Si, which is Si minus its mean value. And so the answer is, well, big with respect to what? And so the answer to that is, well, the only thing that you can compare it with is the average value itself. So therefore, we can make a dimensionless measure of the fluctuation in the following way. I'm going to take SI, Sj minus this thing. I'm going to look at what it is, and then that has units of spin squared. So I'm going to divide it by SI, Sj, and I'm going to call this object Eij. So this is an object that says at the bottom, at the top is the expectation value of the fluctuation of I times the fluctuation of j, and at the bottom is the mean value of I times the mean value of j. Okay, so this is fluctuation of Si, fluctuation of spin j, divided by the average value of Si, the average value of Sj. So that's an object, and why do I want that? Well, because our mean field theory is basically replacing a fluctuation with its mean value. So the mean field theory says if I take Si, Sj, I can think of that as being Si times the average value of Sj, and therefore Si Sj would be just the product. So that's the mean field theory approximation. And so what we're going to do is we're going to look at the fractional error in this approximation. So that's the thing we want to do. And then what is the trick? Well, the trick is that this numerator is just the 2-point correlation function. And so because it's the 2-point correlation function, what that means is that we can use the static susceptibility sum rule to estimate the numerator. So I'm just going to end by just saying, so what is that? How will we use this as an estimator? So then the idea is then we will choose I and j such that Ri minus Rj could be, for example, the range of interactions, or it could be the correlation length. So that would be a way to know how to evaluate it. So that's the first thing. We'll choose a scale, and then the next thing is if we'll call this distance r. So r is equal to Ri minus Rj. So this error as a function of g of r divided by the magnetization squared, we're going to evaluate this in mean field theory, and if ER is much less than 1, then that implies that mean field theory is making a small error, so it's okay. If the error is large, then that implies that mean field theory breaks down. And we have to see what is the criterion for that to be true. Okay, so I'm going to stop there. So next time we will do this calculation, and we will see under what circumstances mean field theory breaks down. And the answer is going to amaze you. Okay, okay, because the answer turns out to be really, really interesting, and I'm not going to spoil it. So, anyway, we will see that next time. Okay.